Hello, my name is Luke Moore, and I'm honored to share the findings of the picosecond test facility at UTA under the direction of Dr. Brandt. Specifically, I would like to present our performance evaluation of microchannel plate photomultiplier tubes when interposing an active ion barrier. In particle physics, detection of individual photons is of paramount importance, so physicists use devices such as the one shown here, a microchannel plate photomultiplier tube, or MCP-PMT for short, to detect them. Figure 1b depicts how the photoelectric effect couples a photon to the release of a photoelectron at the photocathode. An electric field drives the electron toward the MCP and allows us to multiply these electrons. This is an expanded depiction, figure 1c. The MCP produces enough electrons to be detected at the anode and thus gives indirect evidence of the original photon. Quantum efficiency, or QE, is a fraction of photons that produce an electron. In practice, corresponding positive ions from the MCP move in the opposite direction and impair the QE of the tube. This counterproductive process is called ion feedback and is the main cause of MCP gain degradation and loss of QE. Positive ions that collide with the photocathode at high energies then cause more electrons to be triggered and an afterpulse to be detected, as you can see here, figure 2. Preventing MCP-PMT damage from ion feedback is critical for efficiency and functional longevity. The approach shown here uses atomic layer deposition, or ALD, on the MCP to prevent many of the ions from escaping, as you can see in figure 3. Uncoated tubes immediately drop off in QE, while those coated in ALD last significantly longer. Unfortunately, the highly variable lifetimes of tubes with ALD makes performance hard to predict and undermines their research utility. The current investigation sought to determine whether a novel active ion barrier could protect the photocathode from the detrimental effects of ion feedback. The active ion barrier is a physical mesh or grid with variable electric potential shown here between the MCP and the photocathode in figure 4. The higher electric potential of the active ion barrier creates an electric field that drives positive ions back to the MCP and thereby protects the photocathode from secondary electrons. In figure 5, this is the actual apparatus that we use in our laboratory. We use a 405 nanometer laser as our light source. Light passes through multiple filters before entering a fiber optic cable. For compactness, the cable redirects the light back to the detector, or MCP-PMT, that is housed here. The actual afterpulse measurements in figure 6 show the effects of the active ion barrier. With the active ion barrier about neutral on the left, large ions that move more slowly are quite abundant. This peak reflects these major afterpulses. Our lab has previously demonstrated that massive particles such as these cause the most damage. As you can see here, the potential applied to the barrier increases, the major afterpulse peak decreases. Figure 7a shows a general decreasing trend as the grid voltage is plotted against the total number of afterpulses detected. Two essential characteristics of the MCP-PMT that confirm consistent unimpeded passage of the photoelectron to the MCP are the transit time spread and the pulse height distribution. This shows the transit time spread of several different voltages, and it slightly decreases with a positively biased grid before leveling off. Lower transit time is favorable, and the interposition of the grid did not adversely affect this characteristic when compared with MCP-PMTs without an active ion barrier. Here is a plot of the number of pulses detected at different pulse heights for different grid potentials. There is a peak to the positively biased plots around 35 millivolts when there is a photoelectron generated. When there is not a photoelectron, there is a contribution to the noise peak. This is typical of measuring light of low intensities with existing MCP-PMTs. Something different is observed when the grid is negatively biased compared to the grid, as there is an increase in the number of detections at a lower pulse height. Figure 7d shows how photoelectrons colliding with the active ion barrier and can produce a secondary electron that contributes to a smaller pulse height peak. When there is a positive potential on the grid, the electrons cannot reach the MCP and are not detected. We duplicated all these findings in a second MCP-PMT with an active ion barrier. In conclusion, we have shown an innovative approach to protecting the photocathode of an MCP-PMT from the damage of ion feedback by employing an active ion barrier. The active ion barrier decreases the number of afterpulses. Ongoing experiments will reveal the optimal potential of the barrier and test an MCP-PMT with both an active ion barrier and an ALD. Lifetime tests will show the effectiveness of the active ion barrier in comparison to using only the ALD. Future investigations will explore an ultra-long life grid in combination with the ALD. Thank you.